Greetings, everyone. Today we're going to start talking about Chapter 10 on torque. Torque is the first half of Chapter 10, and it is the rotational version of force in a way. You'll definitely see similarities between torque and force. We're also going to talk about the right-hand rule, and I know that most of you will hate it, and I'm okay with that. Remember, I'm giving you a bunch of tools to add to your mental toolbox. We're going to be doing relatively simple examples for now, but eventually you'll be able to combine several different tools together to do much more complicated problems. Throughout this semester, I've tried to show you when we have some quantity that we can replace with another quantity. Early on, I talked about how x can get replaced by theta when we move from a linear situation to a rotational situation. I talked about how v could be replaced with omega, omega being radians per second. A can be replaced with alpha, alpha being radians per second squared. Mass, most recently, got replaced with moment of inertia. Mass is how difficult it is to accelerate something, whereas moment of inertia is how difficult it is to rotate something. Now we're going to be replacing force with torque. That curly-looking T is torque. It's also called tau. T-A-U is how we would spell that. Force is how much effort you're putting into pushing something in a straight line, whereas torque is how much effort you're putting into rotating something. We saw before that we can take our regular kinematics, x is equal to v naught t plus 1/2 at squared. We did that equation to death. We can replace all of the linear terms in there with the rotational terms there. So x gets replaced with theta, v gets replaced with omega, and a gets replaced with alpha. And it still works. That shows you what will happen to an object, how much it will spin, given an initial spin and an acceleration in that spin and whatnot. Very recently, we talked about kinetic energy versus rotational energy. We kept the 1/2s. We replaced the m with moment of inertia. The mass being how difficult it is to move something, the moment of inertia being how difficult it is to rotate something. And we replaced v with omega. V is how fast it's moving linearly. Omega is how fast it's moving through radians every second. Of course, here, the moment of inertia was equal to something. It's equal to, it always ends up being some fraction times the mass times the radius squared. And omega was equal to v over r. Now we're going to do the same thing here with torque. So I'll show you the equation for force, and I want you to think, what is the equation for torque going to look like, given that we replace things like that? What am I going to write down for torque? Pause the video for a second and think about that. Is this what you got? If we can just replace force with torque like that, as long as we replace mass with moment of inertia and A with alpha, we've got it. This is why I emphasize working on these skills. These are all skills that we should always be working on, because the skills that you used here are going to be useful now. It's another good reason not to just brain dump after the end of every test, because if you remember how to use this, then you pretty much automatically know how to use this. Now, there are some new subtleties to it. Torque is the net torque, or the A torque is equal to something R cross F. We'll talk about what to do with R cross F. This is a cross product there, similar to the dot product that we learned about before. And alpha, as you might remember, is equal to A over R, the linear acceleration divided by the radius of the object that's spinning around. There's a lot of stuff here, so let's start by talking about what this part here means. To be perfectly frank, I think that most of you already know that torque is equal to R cross F. I think that's something that you could all get if you thought about it for a little bit and if you knew the definition of a cross product. Let's say that we wanted to unscrew this bolt right here, and we've got this wrench. Well, we want to unscrew it. And if any of you, most of you, already know these things, but if you want to unscrew something, you use the right-hand rule. If you want something to go this way, then you need to twist this way, according to the right-hand rule. Your thumb shows you which way to twist the bolt, or whatever you're moving. So coming up like that, you need to twist this way. Going down, you'd need to twist the other way. And try this yourself. It works a whole lot better if you're using your own hand to do this rather than just watching a video. So get practiced with the right-hand rule, deciding when something is going up or when something is going down. But we know that, okay, we want to unscrew this. So we want to go like that. And so we know that we need to turn this kind of this way. And let's say that I ask you to do this well. I don't want you to waste your time. I don't want you to waste your effort. I want you to figure out the best way possible to unscrew this bolt. And I'm going to give you some options. You can push on the wrench here, or you can push on the wrench here, or you can push on the wrench here, or here, or here. What do you think is going to be the best? Pushing close to the bolt or far from the bolt? Which one is going to get you more, which one is going to use your effort most appropriately at unscrewing this thing? Think about that for a second. Now, is it better to push on the wrench like this, or like in this direction? Or is it better to push in this direction? Or is it better to push in this direction? Do you want to just push the wrench this way to unscrew the bolt? I want you to pause for a bit and think about that. Where should I be pushing, and at what angle should I be pushing? Should I be pushing at this location and at this angle, or should I be pushing at this location at this angle, or this location at this angle, or this angle? Think about that for a second. Okay, well, I hope that most of us recognized that we should probably be pushing around here. Something like this. This is going to get the best torque for us. It's going to provide the best amount of results for the effort that we put into it. If we push kind of perpendicular to the wrench, this is kind of the line of the wrench right there, and we're pushing perpendicular to that. And we also want to be pushing far from the bolt. If we're pushing here, is that going to do anything? If we push on the wrench there, is that going to actually do anything to unscrew that bolt? I really doubt it. We could push there, and that could, be something. We'd get a little bit of effort out of that. But clearly, we want to be as far from that bolt as possible. If you've got something really tough that you're trying to unscrew, you want to get a very large wrench, much larger than this, potentially. In addition, what angle do you want to be pushing at? Pushing at that angle versus, say, that angle? Or that angle? Bringing it up here? What about pushing like this? Is that going to do anything if you push on the wrench like that? Is that going to unscrew the bolt at all? I don't think so. I think that we need to be pushing far from the center, and we need to be pushing perpendicular perpendicular to the line of the wrench. And that's what's going to get the bolt actually unscrewed. That's the only way. Pushing this way isn't going to do much, and pushing down here isn't going to do much. Oh, and last thing, do you want to push with a little force or a lot of force? Well, presumably you want to push with a lot of force to get this thing to unscrew. Well, if we look at the definition of torque, torque is going to be R cross F. This cross, that's a cross product. You can read about it in the book. You can read about all the math behind that in the book. It's also, well, it's either Calculus 2 or Calculus 3, depends on the school. But you'll see that in general, a cross product can be replaced RF sine theta. Remember how we had that work was F dot D, and we immediately replaced that with work is equal to F D cosine theta? We're doing pretty much the same thing here. We are replacing that cross product with a sine of theta. All right. Well, what does this mean? This means that if we want a lot of torque, so torque is the analog to force. Force is how much effort you're putting into moving something linearly forward or accelerating something linearly forward. Torque is going to be how much effort you're putting into accelerating something in a circle. Remember, torque is also equal to I alpha from the previous part. So torque is how much effort you're putting into rotating something, accelerating something's rotation. If you want to accelerate something's rotation, do you want to push at it very close to the center of rotation? R is a measure of the distance to the center of rotation. Here is the center of rotation. So do we want to be pushing at the center of rotation? Probably not. We want to be pushing as far from the center of rotation as we possibly can and still get a grip on this. You know, it's a real object, so we do have to think about that a little bit in these examples. But mathematically, you just want to have the greatest distance from the center of rotation possible. You want your R to be very, very large. A large R will contribute to a large torque right off the bat. You also want to be pushing with a lot of force. If you really want to unbolt this thing, you want to be really working on rotating it. You don't want to just be very gently poking at it like that. That's not going to do much to unscrew that bolt. You want a lot of force. Having a lot of force here will also lend itself to having a lot of torque. Now what about sine of theta? Think for a second and remember, when is the sine of theta 0 and when is the sine of theta 1? Think about that. The sine of theta is going to equal 0 when the angle theta is equal to 0. Sine of 0 is equal to 0. Sine of 90 is equal to 1. If we want torque, according to this equation, we want an angle of 90 degrees instead of 0 degrees. If those are our options, 90 or 0, we want 90 in there because sine of 90 is 1. And then we'd get the most that we could possible out of the radius times the force equaling the torque. Well, that means that theta must be this angle in here. That angle there is our theta. The angle between this R and this F is going to be our angle theta. So, okay, when you are doing a problem, how are you going to figure out what the sine of theta is? What you will do is you will look at your object. You'll see where the force is being applied. Let's say that this is the force being applied. That's the force being applied there. The vector r that we have is going to be that vector there. The vector r is the line connecting the center of rotation out to where the force is being applied. This is vector r. So when you have any problem like this, it's not a bad idea just to draw a line going from the center of rotation out to wherever the force is being applied. This can get confusing sometimes if you've got some sort of circular object like that. And say you've got this circular object, it rotates through that point, and you are applying a force like that. Well, if you're applying a force like that, if you're applying it right there, it looks like the r vector is going to be here, right there, because that is the line connecting the center of rotation to where the force is being applied. We've got this force vector and that r vector right there in this case. Here it's a lot easier because the r vector just follows along with whatever the wrench is doing. The force vector is just whatever force you've got, and so if you can measure the angle between these two this radius and that force, then that is going to be the theta that you plug in there. On the other hand, if your radius looks like that and you're applying a force like that, what is that angle? What is the angle between this and that? Well, it looks to me like that's 180 degrees. What's the sine of 180 degrees? Well, that's going to be 0. So if you push on the wrench like that, it's not going to do anything. It's not going to apply any torque whatsoever. If you pull on the wrench, then there would be a force going this way. And so the angle between this and this is 0, and the sine of 0 is 0. We have to be pushing at a right angle in order to get the most out of our torque. Now, if we had a force like that, or like that, for example, then we could just measure the angle from between the two the two vectors and plug that into the sine of theta. It doesn't actually matter which side you measure the angle. You could measure this side or you could measure this side. The way that sine works, it's going to give you the same answer no matter what. So review your unit circle if that's confusing. But I bet that all of you knew that you wanted to, if you wanted to rotate this wrench, you wanted to be pushing on the outside with a lot of force in a perpendicular direction. And mathematically, saying all those things just means that right there. So that's how you already knew that torque is equal to R cross F. Now, what else can we learn from these equations? Torque with its direction, here I've emphasized, yes, torque has a direction, is equal to the moment of inertia, which is how difficult it is to rotate an object, times alpha, which is the angular acceleration. If you've got a certain amount of torque, a fixed amount of torque, and you increase the moment of inertia, make it more difficult to rotate, alpha has to decrease. And if you're increasing this, you have to decrease this if you're having to keep this the same. If you've got a limited supply of this, then increasing this means you have to decrease that. So harder to rotate, less rotation, less acceleration of the rotation. Keeping in mind those vectors, meaning they have to be going in the same direction. We also have torque with the direction is equal to R cross F. We talked about how that's really just RF sine theta. But let's look for the units of that. The units for torque, so units of torque, are going to be the units for R. What are the units for R? Well, the units for R is meters times what are the units for force? The units of force is newtons. Thus, the units for torque are meters times newtons, but we always just call it Newton meters. The units for torque is Newton meters. For some of you, you've probably seen a little bit of the imperial system, and it would be called foot pounds instead of Newton meters. It would be foot pounds, the distance times the force. But it's the same thing. Now, I have mentioned direction quite a few times going through all this, so we should probably talk about figuring out what the direction of this torque really is. Most people would like to talk about directions of rotating things based on clockwise and counterclockwise. That's where most people have gotten most of their experience talking about rotations. Well, that's fine for most cases. I think that we can all tell that this is going clockwise for one very important reason. It's a clock. But yeah, we can all say it's going clockwise. Okay, well, what if instead of being on this side of the clock, what if I was on this side of the clock? I'm behind the clock now. Well, the clock is wanting to spin around like that, and so that would be around like that on the other side. But to me, behind the clock, I would see this as counterclockwise. If this clock was see-through, if I could actually see the hands on this clock, I would see them moving like this. But to me, that would be counterclockwise. Let's look at this. If the hands on the clock are going around like this, then that, to us now, is now counterclockwise. Seeing a clock from this side means that it's spinning clockwise, as one would expect. But turning the clock around, if it was a see-through clock, you would see it turning counterclockwise. That's something that physicists don't like. We don't like that ambiguity. Like, if you look at something from one perspective, and you look at something from a different perspective, or if some other scientist looks at it from a different perspective, you should both be able to agree which way that it's rotating in this example. It should not be dependent on how you're seeing it. There should be a common language that different people on different sides of the clock can agree upon. And this is what that's going to be. We are going to use what's called the right-hand rule. The right-hand rule is something that a lot of people have used when they're unscrewing something or screwing something in. It's also like righty-tighty, lefty-loosey. So if you screw something in to the right, if you go to the right, you're screwing it in. If you go to the left, you're unscrewing it, righty-tighty, lefty-loosey. For a clock like this, well, you can see that you're going around like this. This hand is going around like that. This is, using the right-hand rule like this, it gets kind of difficult to show. So you're going to need to do a lot of practice with this. The second hand is going around like this. So if I curl my fingers in the direction that the second hand is moving, and then I extend my thumb, whichever way it's going to go, that's going to tell me the direction of the spin of that object. Instead of calling this clockwise, we are going to say that second hand is rotating into the clock. It looks like that. If you take your hands and you put them in the direction that the second hand is going, it is going to be into the clock. Nothing is actually moving into the clock. There's no thing that is moving into the clock. But that's how we can define this direction. Now let's look at it from the other perspective, from behind the clock. The second hand would look like it's moving like that, and so we would curl our fingers in that direction, and we would extend our thumb, and we would say that the direction of motion is this way, out from the clock. Well, that doesn't sound consistent until you start thinking about it like this. On this side, it ticks like this. And so you bend your fingers this way. and you say it's going this way. On the other side, you'd say it's ticking like this. And so you bend your fingers like that, and you'd say it's going this way. On both sides, someone looking at it from this perspective and someone looking at it from this perspective, they would both say it's going like this, like that. You'd be able to quote the cardinal direction. In this case, that would be east. That way is east. So I would actually say that when the clock is held like this, the direction of motion of the hands is to the east. The spin of the hands is to the east. But when I move like this, well, the direction is going to be into the clock or that way through the clock. When it's held like this, that'd be to the north. This is why I said you're all going to hate it, frankly. And I don't not hate it too, I think. The point of this is to give everyone a way of describing a direction to a spin that does not depend on which side of it that you're looking on. That's what we want to preempt here. Now, it's kind of easy to say which way something is spinning when it's like this, because we're used to looking at clocks like this. But what if we had something like this that was spinning around in an arbitrary direction? Or what if we had something like this that was spinning around in an arbitrary direction? How do we figure that out? Well, I just came back from my Lego room, which fancy people might call a dining room, I suppose. Made this. Let's use this to figure out our right-hand rule, or get some practice with the right-hand rule. You can also make something like this to practice with. It's literally just a bar that I can spin like that, but it might help you to practice right-hand rule stuff. If I spin it like this, I'm gonna leave it like that. I'm going to push it on that side. So now it's spinning around like this. Which way is it spinning? Would you call it clockwise or counterclockwise? Well, it would certainly depend on if it's like this or if it's like, oops, like this above you. You know, depending on how you're viewing it, it would be a different kind of spin. And as I said, us physicists don't like having that kind of ambiguity. So I'm going to say that this is spinning in this way. My fingers would curl around this way, curl around this way. You should try to be doing something like this at home just to give yourself practice with the right-hand rule. But my fingers are curling around this way, and my thumb says up. This would be an upwards spin, according to the right-hand rule. Again, nothing is moving up. Things are moving around like this. But someone on my side of this object would say, okay, it's going up. Someone on your side would say, oh yeah, it's going up, like that. Someone beneath it would say, oh yeah, it's going up. No matter where you are relative to this object, everyone is going to say that it's going to rotate up according to the right-hand rule. That is what we're getting after with the right-hand rule, the consistency that we want in physics. Again, nothing is actually going up. There's not a single thing in this whole apparatus that's going up, but it's a direction that we can all agree on to define this. Same way, if we make it spin the opposite direction, so that'd be pushing it on this side around, oops, pushing it on that side around like that, well, we would say, okay, it's spinning around like this. I curl my right hand around like that, and I'd be saying, oh, it's going down now. It's going down because it's curling around this way. You can also think of it going around like that. It's going, if it's curling around like that, then you'd take your fingers, you'd take them this direction, oops, and you'd say that it's going this way backwards now, but if I put it back here, it's going down. This, yeah, okay, I totally acknowledge that this is extremely annoying, but it's the only way that we can define a consistent way of talking about direction. If you try to use, oh, it's rotating left, or it's rotating right, or it's rotating clockwise or counterclockwise, you will always have an ambiguity of which side of it are you on. And talking about left or right when it's in this kind of plane is very difficult to discuss intelligently. It's hard enough to discuss this intelligently if you're talking about clockwise or counterclockwise. The only way that you can talk about this intelligently so that everyone can understand it is to define that kind of thing and say, okay, it's rotating down. Again, nothing is actually going down here. We have just used that as a direction for our convenience. Now let me give you one important word of warning here. When I'm watching people take a test when they have to deal with the right-hand rule, I do kind of think it's funny because everyone is going to be like going like this the entire time and trying to figure out directions based on the right-hand rule that way. And I will always see one person going like this, trying to figure out directions, and that just makes me sad. So don't do that. Don't be the one person that's using your left hand to do the right-hand rule. Use your right hand to do the right-hand rule. Otherwise, you're going to be completely backwards on every single problem that we do. We can use this to figure out torques and all that as well. Well, here's my wrench, and we can use this to determine directions of torques now. Let's say that I'm going to pull on the wrench like this, and I want to determine what the torque of that wrench is. Well, the equation for torque is R cross F. That means that you're going to start with your right hand. This is another variant of the right-hand rule that's pretty much going to give you the same thing. You start with your right hand. You start at the center of rotation. We're going to be rotating at this center. You move your right hand from the center of rotation out to where the force is being applied. Now the force is going to be applied out here because I'm smart and I know that I want to apply the force far away from the center of rotation. And so I apply the force like this. I pull downward on it, on this side. Well, start your fingers at the center of rotation. Move to where the force is being applied. Move your hand to where the force is being applied. And then take your fingers and point them in the direction of that force. Well, what's the direction of that force? I guess it's down. So take your fingers from the center of rotation out to where the force is applied, and then bend your fingers down. Now, I can't really bend my fingers that way very easily, so you have to be a little bit smart about it. Bend your fingers the right way. Start from the center of rotation, go out to where the force is applied, bend your fingers in the direction of the force, and then extend your thumb. And when you do that, you'll see that your thumb goes this way. So it's hard to tell here, but your thumb would go that direction towards that, which is actually north. Behind me is north, so we can call it a northward rotation. Now, if you continued that until you're up here and you're pushing on it like this, so you've got a very hefty bolt that you're really going to have to spin around quite a bit, then you take your fingers, you'd start here, you'd go towards where the force is being applied, then you'd tilt your fingers in the direction that the force is going, which is up now. If it was down over here, then it's up over here. You start here, you go out this way, you bend your fingers in the direction of rotation, and again, my thumb is pointing to the north. So, it's pointing that way. So no matter which side we're working on this, it's going to have the same northward rotation. Even when it's up like this, well, I need to pull it like that, and so that's going to be, okay, taking your fingers like that, pointing them in the direction of rotation, thumb goes back that way, therefore it's north again. If I'm doing the opposite, spinning it around like this, then I take my fingers, I move them to where the force is being applied. Now I'm spinning up around the opposite way, so force being applied up here, tilt my fingers in the direction of that force, extend my thumb, and suddenly it's to the south. I've got a torque going to the south, which makes sense because that's the way, that's the opposite of what we got before. How is that useful in particular with wrenches and screwdrivers and all that? Well, if you've ever assembled anything with one of these, you know that to unscrew something, you take your thumb, you point it, okay, I want to unscrew it, I want to go out like that, so I need to rotate it in this direction, righty-tighty, lefty-loosey again. That will make it go out. So this is lefty-loosey, so it's going to get loose, tilting it to the left. Of course, you all know that when you're on this side, it's actually going to the right. So I've always hated righty-tighty, lefty-loosey because you have to be measuring right or left when it's at the top and not at the bottom, and that always confused me. But the point still stands. If you want to make something go loose, unscrew something, then you're going to have to go around like this. And so, okay, going around like this, well, that's starting from the center, going out, bending your fingers in the direction of the force, your thumb points outwards. That's the way that the screw is going to go. It's going to get unscrewed, screwed out that way if you do that. Screws and bolts and all that are built to be consistent with the right-hand rule. If you look at a screw at very small size, you can tell which way it's threaded. All the threads are going around it in a particular direction. And that direction was chosen so that the screw would obey the right-hand rule. And if you took it around like this, then it would go out. And if you took it around like that, it would go in. So all of engineering is based on the right-hand rule right there. And so that means that us physicists have to talk about it as well, although we really like it, not because of the screws and the bolts, but because it allows us to be consistent and talk about things in the same way, no matter which side of it that we're looking on. So get some practice with that. Seriously, one of the best ways to practice that is to just unscrew things and screw them back in with whatever you've got. I guess this is a wrench, not a screwdriver, but you can find something and practice with that because it really does work in that exact same way for physics, right-hand rule, and defining directions, and for engineering, same kind of thing. You will also be using the right-hand rule extensively in physics 2. So it's a good idea to get comfortable with the right-hand rule now rather than waiting until next semester and being confused by it. So good luck with that. Keep going through all the problems and practice right-hand rule stuff.